Good morning, everybody, and welcome to Mesa Solutions webinar, Power Solutions, Reliability by the Numbers. Before we get started here, I'd like to show you where to ask questions if you have questions during the webinar. If you're on a desktop computer, there should be a little question bubble towards the top right-hand side of the browser. You can pop a question in there. And if you're on a mobile device, there is a little tab that says questions, and you can ask a question within that section there too. The chat is also live, so if you want to use the chat at any time, feel free to do so. Today we have Tom Poteet, who is Mesa Solutions Vice President of Corporate Development. Tom Poteet's role is casting the vision for really the optimal use of natural gas power generation. Within his role, Tom monitors our innovation stream for future sources of site power. He also monitors the development of customized rate plans and progressive field applications, with the goal of meeting our customers' needs and financial preferences. Today, Tom brings with him 40 years of experience in engineering within the electrical power industry, telecommunications industry, and oil field production industry. So we're very honored to have Tom Poteet join us today.
Hey, hello everybody. Thanks for joining us today. We're going to talk about how to calculate the reliability of a combined primary source of power and a standby source of power, and some of the reasons you might want to do that and the value of doing that. So it's important to think about why it's valuable to run the numbers. Suppose your job is to be the person that keeps a plant or facility running, and whenever there's a power outage, everybody comes to you and says, hey, we just lost so much material or so much productivity, certain amount of downtime is very costly. Everybody thinks naturally, well, maybe we need a standby generator of some sort. But you may look into the cost of that, and somebody up in the approval chain says, okay, it's nice that we have that solution priced, but how much more reliability do we really get? So it's not just a simple addition or multiplication. And so we want to run through at a high level some of the important math that goes into a calculation like that. And so you'll be showing you how to take a quantitative approach to that analysis, and then also some of the applications that it can be applied to. So a lot of things go into why you might need a reliability, a standby solution. Your utility might be making changes, hopefully improvements to their system. Those could be on the transmission system or in a substation or even out on the distribution lines, but it still doesn't necessarily protect you from a very local outage incident. Maybe a vehicle hits a pole or something like that, not too far away from your facility. And there's a variety of standby solutions that you can look at that have various connectivity options. And what we're looking at today is a very simple standby solution. We're looking at, what if you're connected to the utility and you have a standby generator in place that comes on if the utility goes off. And just to give you an idea of the order of magnitude here, we'll be looking at a simple example where suppose the cost to your company from outages on the utility system, maybe they total $2 million a year. We're going to look at an example like that. And in this example, the backup system costs about $3,600 a year, or $360,000 a year. And so that would give you a savings of over $1.5 million if you had a system like this. So it is a simple example, but probably the majority of standby solutions that are out there would fall pretty closely in this type of analysis. So right away, we'll just look at some of the different mathematical concepts. If you want to know what's the reliability overall, if the utility's reliability, in addition to my backup system's reliability, it's not just additive, it's not just multiplicative. There actually is a well-known formula for calculating that. And if you look at it just by inspecting that formula, it makes sense. Basically, it's the reliability of the primary system plus the reliability of the standby system when the primary system is not running. So in this case, our primary system is the utility. The secondary system is the standby system. So talk for a minute just a little bit about the difference between availability and reliability. Availability is a pretty simple concept that most people in industry use. It's basically just out of the potential hours in a year, how many hours is the system up and running. We often just call that uptime. And for a computer network system, for example, we might say, hey, we want 6 nines of availability for our computer network. And it's kind of that same sort of concept that we're thinking about. Reliability per se is a more intricate theoretical statistical approach where maybe if you have individual components that you manufacture in high volumes and use over regular periods of time, you can get into good statistics on how often those things fail. And it ultimately, reliability comes from calculating the average time between those failures. In this case, we're wanting to use availability as a surrogate for reliability, and that makes a lot of sense when the time between failures is relatively long and when the repair times to the system are relatively short, and especially when you're referring to an overall aggregated system. A generator in an enclosure is a good example. An automobile is another example. If you think of it from the automobile example, you don't necessarily, the consumer doesn't necessarily want to know what exactly is the reliability of all the components of the air conditioner system and all the components of the steering and brake systems. What you really care about is, did your car start and run? And you might have, in a complex solution, you might think, well, I really value the brake system more than I value the air conditioner. So you can get into a pretty complex analysis of that type of reliability. So what we're talking about is the reliability of an overall set of components viewed from the perspective of availability. And with these characteristics, we can use availability as a surrogate for reliability. So from the utility side, most utilities will publish data that talks about the reliability. They look at it from several different ways, and you've probably seen the acronyms if you've looked into this, SAIDI, SAIFI, CAIDI. Those are all different names of different indexes for use for determining from a system perspective or from an individual consumer perspective, how many outages per year does a location experience, and what's the duration of those average outages. So if you're looking at a greenfield system, you might want to look at the utilities published data just to get a starting point. But if you're talking about an existing system, you can certainly just take that location's experience of how often and how long are the duration of the outages that they experience. So in our simple example, we'll talk about a utility system availability where suppose your utility at this location has 4 outages per year, and the average duration of each outage is 2 hours. And so that gives you a total of 8 hours, and just calculating the ratio of outages to overall uptime, it gives you an availability of 0.999087 in that case. So 3 nines of availability. And suppose in this example that when you do experience an outage at your facility, that it cost you $250,000 per hour for each outage. So in this example, the annual cost of outages is $2 million. The standby system, suppose the individual availability of a generator is 0.997. In this example, we're just looking at like a 400 kW generator. And for the load, maybe we just need one generator and perhaps we want to have an N+1. So there's two total generators. And just using notional numbers, suppose the cost to lease one of those generators is $180,000 per year. So your total lease cost would be $360,000. So just comparing those two numbers, the utility cost versus the standby system cost, you're looking at a savings of $1.64 million. So clearly that's a simple scenario, but it tells you the order of magnitude of the numbers involved. And just to get a little deeper in the math for just a really short moment, one way that you can model the reliability of the standby system, if you have N+1 or multiple units that add up to your N, you fortunately Excel spreadsheets have this formula all set up for you, but it's the same calculation that you may remember from a statistics class, where maybe the problem is if you're going to flip 4 quarters, what's the probability that 3 of them will be heads? And the exact same math, and it shows that with using this formulation, if you only need one generator in and you have 2, the probability of one of those being on is very high. So when you put that all together, you put that together with the reliability of the utility system in our example, you really have a tremendous amount of reliability. I think that's 8 nines. You probably don't need that much. So in that, if it calculates out that way, you might say, well, I don't need N+1 for my standby system. I can get by with just N. And graphing this out, looked like as we were preparing for this, it looked like the simplest way to show some comparisons is looking at it, all things being equal, except for look at different cases of the number of times per year that the utility experiences the outage. And what this shows pretty dramatically from the number of nines that you get versus the outages per year, the effective reliability of just the utility really goes down, straight line down, as the number of occurrences of outages go up. But with a standby system, the overall reliability to the load stays very near 100%. And looking at the same numbers, just the cost, you can see that with the standby system, the cost is basically held to the cost of that lease. And whereas if you're just utility only, every time you have an outage, you have that cost, and the more outages you have per year, the more that multiplies up. So another case that's important to look at, and this may be what most people are ultimately interested in, depending on the criticality of what your site is doing. But you might think of a standby system as insurance for an extraordinarily long outage. So by that, I mean, the utility indexes might show that the average customer on a given utility system might be out for 50 to 200 minutes a year. Your own experience might vary, but it's not bad to think about every 4 or 5 years. Just about any utility system might have a storm of some sort or an event of some sort come through where some of the customers can be off for 2 or 3 weeks. If you live in the part of a country that is subject to ice storms or tornadoes or earthquakes, then there could be significant damage to the utility system. And all of a sudden you get a really long outage. So we're still just looking at it in the conventional way of, cost of material, lost revenue, lost productivity. But you might think about it, if a site's off for 2 or 3 weeks, how much damage does that do to your whole business? So in this, using all of the same numbers except for the length of the outage, we see that the cost of that insurance for a long outage is still the $360,000 per year. And even with that long outage, theoretically, the system could still be down a little bit, but that just the cost of that outage would only be about $756 in our calculation. So it certainly behooves you to think about what is the criticality to my business of experiencing a huge long outage like that every 4 or 5 years. It's definitely a consideration worth looking at, certainly for your diligence, but also because the cost to cover that is really no greater than just covering the cost of simple, I'll call them steady state outages or routine outages. One other thing that we'll mention briefly, if you happen to be in a part of the country where there's a deregulated market, there's also additional revenue that you can gain if you have a standby system involved. Your utility may have demand reduction programs that you can enroll in, various demand management things, other kinds of ancillary services. Those are certainly things that can add to the value of a standby system. But in many places, depending on how much it costs you to have an outage, it's possible that those numbers could pencil out just for standby. So we'll look back to Amber and see if we have any questions. And looks like we have about not quite 15 minutes for questions. So.
Yeah, Tom, someone mentioned what really does a decimal point do? How does it affect the output really? Like 0.999 versus 0.995.
Right. So a really good example, the easiest way to look at it is, I use the example of if a lot of people in their contracts for network administration will say we want 6 nines of uptime. If you just calculate the ratio of hours on to hours available, 6 nines of availability equates to about 30 seconds of outage per year. So as you start dropping nines, it's very simple arithmetic to figure, but it goes from 30 seconds to minutes to hours as you reduce your nines.
Thanks, Tom. Another question someone popped up in here. So this plan you have laid out here seems only to cover the upfront costs. What about some ongoing expenses? How do they factor in to your analysis, like fuel or maintenance, that kind of thing?
Sure. So for purposes of this webinar, I kept the model really simple. In an elaborate model, you can certainly figure in the cost of fuel if the standby system is running. If it's just running for a few hours per year, the cost is not going to dominate that. But if you do want to plan for one of those major outages, you could certainly add in a characteristic for what the fuel cost would be. Also, depending on how you obtain your standby services, if you do a lease that a monthly lease for multiple years that includes maintenance on the system, there may not be any other numbers for the consumer to model. If you're looking at buying a system and then contracting for the maintenance and maybe some split on repair costs, then you would need to figure those in. But the concept that we have modeled here is pretty simple and is certainly available.
Great, thanks. So yeah, I actually have a question. You went into some depth with the equations, but can you speak more to the equations that you're using? Like
Sure.
someone who doesn't quite understand it as well as maybe you do, because I for sure don't.
Sure, yeah, it's something that's pretty interesting if you like math, but that overall reliability equation, that branch of mathematics actually comes from the mid 20th century when rocketry was being developed, and the engineers were trying to how do we make rockets more reliable? And one of the things they encountered after component failures was, hey, it turns out if we just use two regular components in parallel, for example, rather than having a more expensive single component, the reliability can go way up just because of probabilities. All of this actually comes from probability mathematics. So that from the mathematical perspective, the scenario that we're looking at is called simple switching. That doesn't mean in electrical terms, we often think of instantaneous switching or fast switching. It's not that. It just means mathematically it's simple switching. And what it means is that you have the primary source and the standby solution, and mathematically you're looking at the probability. What is the probability that either the primary system is up or the secondary system is up when the primary system is down? So in simple switching, you only have one system going at a time. They're both either, when they're off, they're completely off. When they're on, they're completely on. And they're both able to handle the load in question.
Great. Thank you. We do have another question. Can you give what a typical lease term might look like that Mesa offers for some standby applications?
So the best value is to think in terms of multiple years. And a lease like that can be configured if for the right parties in the right scenario. You could look at that as a capital lease or just a normal lease. But multiple years, it's kind of depends on what the customer wants. But 3 to 10 years is terms that are often discussed.
I have another question for you.
Okay.
Brian is asking you to elaborate, if you can. What are some savings potential clients might have using these systems for peak shaving as well as standby, and have we factored in such systems?
So this model doesn't factor that in. I just wanted to show a simple case of most of the country is not in competitive electrical marketplace. So what we wanted to show in this simple model is that even if you don't have a competitive power for market, you can still, depending on what your work is, how much the cost of the material that you have in your plant or other factors that create costs related to outages, you can still show an economic benefit by having a standby system. And so that in some cases, the cost per hour of an outage to the customer may be what dominates the math. In other scenarios, it may be how big is the load or how small is the load overall. But just some orders of magnitude, if you have a standby system that and you're in a deregulated market, and the utility or the operating authority has programs you can roll in, just the order of magnitude that people usually calculate for something like that is a potential benefit if you enroll in multiple programs, just an order of magnitude of $50,000 to $100,000 per year per megawatt of installed backup capacity. But there's 20 things that affect what that number actually is.
We do have a question from someone in the question chat there. How many, if this were you and you were, say, a grocery store owner or something, how many generators would you recommend for a situation for some backup power?
So I think the way to look at that is, a grocery store is a good example. If you want to make it easy to work on the units, do maintenance on them, and make the mathematics work in your favor for sort of that N+1 scenario, it's probably good to have 2 or 3 or 4 units all running that can run synchronized together in your standby solution. Suppose the N is that you just need 3 units to cover the load. With an N+1, you get very high reliability. As I mentioned in the model, in the mathematics of this shows that the utility system reliability plus the standby system might be so great that you can get by without a +1 or a +2 for routine outages. But if you really want to cover that, what I call the insurance for the catastrophic situations where you want to be ready for a 2 or 3 week outage, then that N+1 will really, it's not that much more expensive. And with this analysis, you can tell how much more reliability do I get for that. And the reliability is very high.
Thanks. Yeah, it doesn't look like we have any other questions, but I actually kind of have a question because it's kind of been lately, it seems that there's been a lot of kind of natural disasters, lots of flooding, lots of fires, and that kind of thing. And we hear things like 50-year flood or 100-year flood to describe those events. Is there a way to describe or how we can predict a 200-hour outage to occur? How likely is that? And is that something I can prove to my management?
Well, if you can get your particular utility to share their data on long outages, that would be the first place to start. Interestingly, in a lot of utility jurisdictions, the reliability index numbers that utilities are required to submit, often their corporation commission might say you don't have to report catastrophes, so because it's not routine enough. So you can argue that both ways. If you're in an area that experiences a lot of tornadoes every year, maybe the corporation commission doesn't require you to report outages based on tornadoes. So the utility is probably the best place to start with those numbers. If it's an existing plant, the local plant employees can probably give you pretty reliable, even if it's anecdotal data on, every 3, every 4, every 5 years, we have an outage of at least a week because we have an ice storm that's really bad. Or maybe they'll say, we've been fortunate the last 2 storms didn't get us, but they may be worried about the next one. So different parts of the country seem to be affected more or less by weather. If we're going through a decadal period of a lot of hurricanes, then folks in lower lying areas might want to think more heavily about getting a standby system, because we know, you can read in the news of many cases of people who are out for 2 weeks or 2 months or something like that.
I think we have time for one more question.
Okay.
How does Mesa respond when someone says that diesel generators are really the best form of backup power? Because it's not intended to run for long periods of time as a backup generator. Fuel savings might not be the key benefit in this situation. One benefit is maybe fuel at the site. Natural gas is readily available. What other benefits do you see for gas generators?
Yeah, sure. So several things. I kind of work backwards from the way you asked that. The units that we have can run on natural gas or propane. So if you're in a situation where maybe a local jurisdiction requires you to have some standby fuel stored, you can accomplish that with propane and have it hooked up also to the natural gas system. And as long as the natural gas delivery system isn't interrupted by something like an earthquake, you've kind of got the things covered from both directions. And of course, the cost to maintain a stored amount of propane is a lot simpler than long-term storage of diesel. Of course, you want to get a natural gas generator that is very reliable. Obviously, we stand on our reliability, or we wouldn't be talking about this. But it's got to be reliable for starting. It's got to be reliable to keep running. If you have a very small load, then you might look at, if you have a small load and your load's not that critical, then obviously you might look at other economic situations. But if your load is relatively large and relatively critical, and you want to have a solution that not only can handle short-term outages but long-term outages, our units are good for that, because our architecture is basically a prime power architecture. So if you do get into the scenario where there's a large, long regional outage, then you can still use the generators that we've provided for the typical standby. All right, Amber's given me the high sign that we are out of time. So thank you very much for talking to us today, or listening in, and would love to hear your feedback and any additional questions that you have. I think we've got a slide here with an email address you can use. I maybe already passed it. Oh, there. Okay, Amber's giving me instructions. There you go. So if you have any questions, would love to hear from you. Please let us know. And in real life, most scenarios are going to be more complex than the ones that we looked at, but the math is not prohibitive. We just need to sit down with you and talk about your specific location, and we can tell you how much reliability you actually should expect for the amount of dollars that you put into your system. Thanks again.